All right, well, try this. Welcome. Thank you so much for joining us. We are coming to you live from the RV Falkor in the Pescadero Basin out in the Gulf of California. And my name is Becca Shepard. I'm a science educator along with the science crew. And then vents are always exciting. For those of you who aren't familiar with hydrothermal vents, those are places where seawater has circulated down through the sediments of the ocean floor, have been heated by a heat source that is a piece of mantle that has actually come up near the surface. And that's happening here in the Pescadero Basin because the movement of tectonic plates is actually stretching Earth's crust thin here. So as that crust gets stretched thin, the mantle comes up close to the surface. That circulating seawater gets heated up. It dissolves lots of compounds, and then because it's hot, it comes back up towards the sediment surface and vents hydrothermal fluids into the ocean. So not only is that cool in itself, but now you've got hot hydrothermal fluid coming in contact with very, very cold ocean water. Compounds to precipitate out, forming cool mineral structures. And those dissolved compounds actually support life. They support chemosynthetic life, which is a way of using inorganic compounds for energy, as opposed to having to rely on the energy from the sun, like in photosynthesis. So hydrothermal vents, awesome, right? Ecosystems, amazing. But what was special about these? The Akka vent field is different than if you're familiar with black smokers. Black smokers are a type of hydrothermal structure that is formed when we bring up lots of sulfides. Iron and zinc, for example. Black smokers are laid out as a structure. Here, when we bring up, we precipitate hydrate carbonate. Perfect. So here we're actually precipitating anhydrite and carbonate, which are light-colored minerals. And this is a new thing. These are also fairly deep. So the combination of those unusual minerals and very deep and a very diverse community is what we've come to see. So enough of me talking. Let me show you some video. Can you send me up the brand new vent field? So while Monica loads that for you, I'm going to show you some video of a brand new vent field that's already been discovered on the first leg of this cruise. We came out to map what had already been found and to look around the area to see if we could see something similar. So here you're getting an up-close view of that brand new vent field. You're looking up a hydrothermal chimney. Some of that fuzziness is microbial mat. And then if you look at where the water shimmers, that's the very high temperature hydrothermal fluid coming out the top. These structures aren't always chimneys. They also can build really beautiful other structures like that cave. And as I said before, through chemosynthesis, they support a diverse ecosystem. So lots of tube worms. This is Oasis. This is actually a very rare tube worm, but that's very, very abundant here. We see lots of anemones, crabs, lots and lots of microbes. Our biologists are actually really, really excited. Then I'm going to show you one other video, which is an up-close view of a very unique structure. We actually call this an upside-down waterfall. This was also seen last week. What you can see here is that sometimes that hydrothermal fluid starts squeezing out the side of a chimney. And that causes the minerals to precipitate out sideways, kind of like a table. And that means that those fluids then keep having to go farther and farther out under that table. And the surface underneath there shimmers. It almost looks like a mirror. And that's because as we look at it, the difference in the optical properties between the very hot fluid and then the cold ocean causes that shimmering effect. Absolutely gorgeous. So that's what we're working on. But of course, our team of geochemists, biologists, microbiologists who are trying to understand how the organisms live down here, how they are distributed.
Falkor, I'm afraid it looks like someone accidentally muted you on your side. Can you guys turn your audio back on?
Can you hear me now?
You can. Thank you very much.
Excellent, great. All right, well, welcome back. Okay, so we have the ship that we're on, which actually can also do some mapping for us. We've been using AUVs to do meter scale, so like 3 feet, resolution mapping and exploring new areas. And then if I can have the next slide. Well, that's just a picture of that AUV actually in the water. And then, of course, the ROV Sebastian. Now, I have some folks with me who are going to talk a lot more about that. But from our perspective, we've had, for the first half of our cruise, a high-tech imaging system that is allowing us to create a high-resolution map of this vent field. Centimeter scale resolution, and that's never been done before. Really exciting. That map is helping us do the biology, map out the biology at a scale that's never been seen. So enough from me. I want to hand the mic over to some folks who can tell you a little bit more about that tech. So, Russ, you ready to take over?
Yeah, I'll take over. Hi there, so I'm Russ. I'm dealing with the ROV. So as you can see in the picture we had there, that's Sebastian. Rather special vehicle. It's able to take a number of different scientific equipment. We can integrate pretty much everything that the scientists throw at us, and they tend to throw quite a bit at us all the time. So Sebastian's actually, she's connected to the ship. We've got a nice winch on the top. We've got our umbilical that goes all the way down to Sebastian. So she has a solid umbilical, because obviously we're working in hot vents, so we don't want something that might get damaged or burnt in the heat. When obviously the vehicle itself has 2 manipulators in the front end, and we have a small tray. The small tray allows us to, as you can see in the video before, you see the core tubes. All these different items can actually be placed on the tray, and we can actually have them all set up for different science missions. So every mission's different, so we can actually adjust all the equipment to suit the mission. Just trying to see, yep, and we can see we've also got, obviously the video we're getting here, we've got a number of cameras on the vehicle. There's one that's very, very unique. We've got the 4K camera. That produces the ultra clear video that you can see obviously on YouTube and Facebook, and obviously on our website. We have a number of other cameras which we configure for viewing different tools, or if we want to do different tasks, we can actually configure them for that. So what I'm going to do is I'm going to pass you over to Debs. She's going to explain a little bit about the data and what we actually do with it on board.
Thanks, Russ. Yeah, so as you can imagine, with all of the technology on Sebastian, there's also quite a bit of data that comes up from Sebastian. So we monitor everything that's going on with the vehicles. This helps the pilots know whether there's any kind of issues with the vehicle, whether they have to go back and look at whether there's any kind of issues that they can troubleshoot. We also collect all the video data. So all of that video data comes up through that umbilical cable, and we record it as it's being collected. We record 2 different camera feeds at a time, and that, especially the 4K, can be very large in size. So we have a number of systems on board that help us manage both the large volume of data we're collecting and as well transferring that back to shoreside, and as well for the principal scientists to take home with them. We also collect all of the CTD, so conductivity, temperature, and depth, and dissolved oxygen information that the Sebastian has. It has a sensor on board that reads that information. So we can make profiles as Sebastian's diving down to the seafloor and then as it's coming back up. And we also record all the navigation data. So there's lots and lots of different types of data fields that we're recording in real time, and then also using some post-processing information to sort of help troubleshoot or to just sort of diagnose things in the future. And scientists as well can use a lot of that, both the high temperature probe. The vehicle has a high temperature probe, as well as a number of other sensors where they can use to help figure out what exactly is going on within the vent field. One of the other few things that we do is also live feed this information to you guys. So you can watch it on YouTube and Facebook a lot of times live. And that's also something that somebody monitors. And we get to basically choose many different types of video feeds from the ship as well as from the vehicle to help give you the best picture of what's happening on the ship.
So can you explain to them? Explain to them.
Oh, yeah. Oh, sorry. So we're actually going to take a little trip through to the control room so you can see all the fun stuff. So we're just about to change over to a small tablet, and I'm going to actually put some earphones on so you can actually hear what I'm saying. And we're going to show you around the control room. So just give us a second. We're just going to move across there now.
For those of you who have not been on Russ is taking us right now. You can see down that corridor. Oh, there we go. Take it over.
Testing, testing. 1, 2, 3. I can hear it. Hello? I'm not hearing anything.
We can hear you, Russ. Well, Russ gets that. Russ, can you hear us now?
Yeah, I can hear you now. That's looking good. All right, so we're heading into the control room. So this is where all the magic happens. So in here we have, obviously, there's quite crowded right now, but we've got, this is our science team, and we've got our ROV team. So in this area here, we have, this is where the pilots sit. We've got our chief scientist sitting here. You can see all the screens. We've got a multiple of information up here. So as you can see, if you can look over here, the guys are actually taking some samples right now. And there's all the cameras are configured so the guys got a good view of all around them, so they can actually do the manipulator work, etc. So if we want to take a little scan around the side here, these are actually the science team. They've actually got their screen set up so they can log data. So they've got their loggers up there. They can actually take their sample readings. They can, whatever they want to do, they can actually get it up on their screens. If we come across here a little bit, we can actually see the guys working on the arms. There's James here. He's actually taking some samples. And we're using these Titan 4 arms. These are actually a Schilling product. Excellent arms, I might add. But you can see we've got 2 of them based up front. This is actually looking down on the tray of the vehicle. So we've got a couple of bio boxes there. We've got our 8 push cores and a couple of baskets, so we can add things like rocks or any sort of hard samples that we want. And over here we have our video suite. This is where we take all our high definition video. Also, we've also got sonars and our ship's navigation controls there as well, so we know where we are, so we don't get lost. So we're just going to head back over to the library, and then we can get some questions and we can answer them for all you guys that are interested in what we're up to. Just making our way through the rabble of people.
It's on, video is on. Turn this off. Is it still on?
I think it's still on.
All right. Can you hear us again? Back on this system?
We can. Sounds good.
Excellent. Well, it sounds like we're ready to entertain some questions if we have some folks out there with questions.
Well, I have one for you just to sort of kick things off. Obviously, the deep sea environment is quite an extreme environment to work in with any sort of robotics. Do you guys have to make any sort of adjustments when you're dealing with the extreme heat from the hydrothermal vents as well as the extreme cold from being that deep?
Yeah, there's several things that we do. Obviously, we don't want to fly the vehicle into the thermal vent because there is some things on it that are susceptible to damage. But we tend to use materials that are very resilient to heat and have got a wide temperature range. So, but there is obviously situations where you don't want cables getting near that, electrical cables. Most of the stuff that's used for the hydrothermal vents will be titanium, or they'll be wrapped in like a Kevlar style protection, or we'll use a stainless steel material, something that will actually not melt. So you do have to make considerations for how you set up the vehicle, but most of the equipment that we'll use will be designed for extreme temperatures, basically, and extreme pressures.
Great. And while you're up there, could you talk a little bit about how the process of getting the robots in the water and out of the water, what that takes from the crew and the ship?
Yeah, so basically for a launch and recovery, you would have basically 2 ROV guys on the back deck. We also have 3 deck people. So we have the situation that works is you have one guy that operates a winch, and there's obviously myself or another, which would be managing the deck and also assisting with the floats. Because as you know, it's a solid umbilical. So what we have to do to make Sebastian be able to fly around from the vessel, we have to add what's called a catenary, or a float system. So we actually add approximately 12 floats to Sebastian, and they're spaced in such a way that it gives you about 130 meters of excursion. So it basically allows the umbilical to float up above the vehicle, and it allows you a bit of a buffer zone. So if the ship's coming up and down, it doesn't snag the vehicle, because if you're doing something very sensitive, you don't want to get pulled off the actual job site. So when we're actually doing that, obviously we have 2 people that are putting the floats on. There's one person that's looking after the umbilical, and then we have a deck officer who's managing all the winches and the A-frame. So that's kind of how we'd set it up for launch. And then the reverse would be for the recovery. But once it's actually in the water and it's actually going down to the actual area that we're interested in, we can reduce the number of people on the deck. Because all we then need is we need a guy on the winch. We usually have a nice little barrier put up, and then he can just operate the winch all the way down to the bottom. So that's basically the basics of it.
That's really helpful. And to give a little bit of more background information, or to get into sort of what you were talking about with the tether and the umbilical, if the robot is actually able to go down 4,500 meters, that means you guys have to have at least that much umbilical on the ship, yes? Like, how is that stored, and how is that processed out into the water to the robot?
Yeah, so what we actually have is up on the upper deck, we have a large winch. So on the winch, we actually have just shy of 5,000 meters, of umbilical. Oh, here we see here. So I don't know if you can see this picture. This is actually the A-frame, and you'll see this cable coming down from the A-frame to this docking head. So this is the area that Sebastian would dock into when he comes on deck. But this is the cable, so it actually runs up to the winch. So basically, you have over 5,000 meters of wire available so that we can go down. I mean, his actual depth, Sebastian is able to go down to 4,500 meters. That's our maximum depth. So we've got a little bit spare just now, still in the drum.
Great. We actually have a bit of a shift. We have a question from our audience, and it asks, how are your manipulators waterproof to handle the pressure at this depth? At 3.7 kilometers, is that how deep you are right now?
That's correct. So the actual manipulators themselves, the mechanics behind the manipulator is the hydraulic, so that's filled with fluid. So what we do to compensate the electrical part of the arm is we actually use the same hydraulic fluid. And we actually have, basically on the connection to the hydraulics, we have, think of it like a bladder or a balloon. If you think of it very simply like a balloon, it's filled with oil and it's attached to the arm. So as it sinks down through the water column, the pressure of the water acts on the balloon, and that then pushes the same amount of pressure back into the arm. So you don't have there's not a big differential, thus it doesn't crush. So that's basically how anything that's electronics or electrical, we actually fill with a fluid. Either it be a silicon oil or a hydraulic oil, and it will actually be open to seawater so they can actually receive the pressure from the seawater. So as it goes down, it equalizes.
Wow, that's fascinating. I didn't realize there was that much go-between between the two. That's really interesting. To go back a little bit to the umbilical, and maybe this is something we can bring Deb in as well. Everything that goes back and forth between Sebastian comes through this umbilical, yeah, comes through this tether. So can you tell us a little bit about what it consists of and then what kind of data it actually brings back and forth?
Yeah, so I'll go right into a little bit about the mechanics of it. So basically the tether itself is, internally it has a little tube with some fiber optics inside. So that allows us to transmit data back and forward. Round about the tube, we actually have some electrical conductors. So that allows us to send the electricity from the surface down to the ROV to power up the motors to run the hydraulics. And then on the outer side, basically the outer surface, there's an armor wire. So the armor actually gives it the strength, so it can actually hold its weight over that distance. And what I'm going to do is I'm going to pass over to Debs, and she's actually going to explain some of the data that actually comes up and down the fiber optics.
Thanks, Russ. Yeah, so what comes up through those fiber optic channels are all of the video, all of the vehicle information like the comps and the electric information, the translation down to the actual arms, any scientific sensor plugged in to the vehicle. So there's a number of scientific sensors that they can add. Scientists can bring sensors. So all of the data that gets plugged into the vehicle also comes up through that umbilical, and we record all of that data. So there are, I think, something like at least 6 video feeds that we get up through that umbilical, as well as a number that are just for the vehicle to sort of be aware of where they are. There's a little camera on the manipulator arm. So there's lots and lots of different parts of the vehicle that send data. And all of that data that is about the actual thrusters and how much pressure is left on the vehicle, all of that gets brought up through that umbilical and then also recorded. And so the biggest volume of data, I would say, is probably some of that 4K data. So 10-minute video is about 4 gigabytes of space.
Wow, that's a
Yes.
massive amount of information. And then you've also got the sensor readings and things like that. I would assume that bringing that much information, one, takes a lot of processing power, but two, organization is, when you're gathering this sort of data, is it stuff that you tag as you go along? Is there sort of an infrastructure set up that you store certain aspects, certain places, or is that all the above?
Yeah, a little bit of all of the above. The video data gets logged through a video machine, a video recording machine. So like I said, we are recording 2 video feeds. We get to see more cameras from the vehicle. We actually get to see every camera that's being sent up from the vehicle, but we're only actually recording feeds from 2 of them. And then all of the data about navigation, vehicle thrusters and comps, and all of that vehicle information, as well as all of the scientific information, gets sent into our scientific computing system, which then logs it into files, basically text files. And then all of this architecture gets put into a cruise data archive structure, and then it gets copied at least 3 more times on sort of backup drives, as well as a drive to the shore side and the drive that the chief scientists will take home with them. So there's a lot of data being pushed around the ship. I think right now our current cruise size is somewhere around 11 terabytes. And that is with all the AUV data that the scientists collected, as well as all of the mapping data that they collected with the ROV in the previous last couple of weeks, and then all of the video data we've collected so far. So yeah, we're hitting about 11 terabytes.
Wow, that's a lot of information. We're getting a couple other questions more along the science side. We had someone type in, it looks like the chimney structures are rather delicate. How intense is it piloting around and attempting to take samples from them?
That's really for you.
Some of the chimneys can be quite delicate, and it's very difficult to tell when you actually fly up to them. So you really have to be very aware. We use a lot of the sonars, we use obviously a lot of cameras, but it's until you actually get up to the chimneys, it can look like solid rock, and yeah, you touch it and it's like paper. So it really does vary a lot. Maybe we can pass it on to the science, and then they can let us give you an idea of the sort of makeup of it and how it works.
Yeah, so it's a great question because it's actually a little bit tough to answer. It really is variable. Once you get into the main part of the structure, they're fairly solid, but the outside often crumbles. So there's many times that the scientific team says, let's try for that chunk that looks like it's going to come off in one piece, and just goes to little tiny bits and pieces, and we have gravel. It's often very tough to predict. So yeah, and it runs the gamut, and that's one of the challenges. As I mentioned very early on, we were taking core samples and specifically looking for places where we have soft sediments, because in a hydrothermal vent field, that can be more rare. So yeah, it runs the full spectrum, because remember, the vent field is not just the chimneys.
So can you give us sort of a little insight into what these chimneys are that we're looking at? Are they, I mean, Russ mentioned that some are more solid than others. Are they minerals? Are they solid deposits? Are they old? Are they new? Are these too many questions for you all at once?
No, no such thing as too many questions for a scientist. Are you kidding? Yeah, those are great questions. So actually, the age of the chimneys, let's do that one first, because that is currently a hot topic of discussion amongst the scientific team. That's one of the things we're actually trying to learn on this expedition. This vent field may be very unique because we suspect it might be a slightly more mature system, an older system. A lot of the vent fields that have been studied at other places are very young and often don't last very long. Whereas this one, we think older. But again, first of all, to a geologist, always say, do you mean millions of years or just tens to hundreds? We think maybe in the hundreds to thousands of years for this vent field, but we don't know. We're still looking. In terms of what they're made of, these are very unique. As the hydrothermal vent fluids start to precipitate, the first mineral that comes out is anhydrite. That's a calcium sulfate mineral. Once you have a channel on the inside of the chimney and the vent fluid isn't mixing with the seawater directly, we start to precipitate a lot of calcium carbonate. So we have a mix of minerals. What's missing are those metal sulfides that we're used to seeing at black smoker systems. Here, we think that the traveling of the hydrothermal fluids through a thick layer of sediment is actually causing those metals to disappear, to precipitate out further down. So there may be some very interesting metal deposits below the ground. So that changes the chemistry of the whole system.
Wow, so it's a pretty complex, it sounds like there's a lot of stations in this. It's not just a hole in the ground that stuff's coming out of. There's a lot of processes that happen in multiple areas that affect the whole system.
Oh, definitely. And that's one of the things that makes the distribution of life very, very interesting here. Because if there's one good rule for these systems, it's that those geochemical gradients, how the geochemistry changes over a space, both vertically and horizontally, that's controlling how these organisms can set up their ecosystem.
That sounds absolutely amazing, and I really want to get into that, but we also just got a question about the ROV, so I kind of want to make sure that our audience gets taken care of before we go to another thing. But please, Becca, keep that in mind, because I definitely want to revisit that. Russ, we just got a question that was more in your backyard, asking about the power losses over the umbilical. How do you get all the power you need down through the umbilical over those distances?
So what happens is we have basically a transformer station on the ship. So what it does is it takes in, say, for example, 430, 440 volts AC. It steps it up to 3500, and then we're able to do like a high voltage distribution down to like another transformer in the vehicle, which then step that back down to a usable voltage. So basically the way we get around it is we step the voltage up to a higher voltage, so we get less transmission loss, basically. So that's how you get around your losses. So you have to go to a high voltage, which means we have to have a lot of protection and a lot of safety put in there. But that's essentially how we do it. It means then the conductors can be smaller. It means the actual umbilical can be made smaller diameter and a little bit lighter. So that's exactly how we actually do it.
Well, and forgive me if this is a basic question. This is coming from me personally, and I am not an engineer or mechanic, but don't you have to be a little wary of having a highly electrified metal coil around itself? Do you have to deal with any sort of magnetic or other side effects?
We have actually a shield. It's actually shielded, so you the cables themselves have all got grounding wires and a shielding case on it, so it's all drained off. So any coil issues you have is drained off the ground, so we don't have any issues. And because we use, obviously, we're a fiber optic age where we don't use coaxies anymore, we don't tend to have that problem with the cables anymore.
Gotcha. Thank you very much. Appreciate you for putting up with my novice questions on there. Is it all right if we grab Becca again and go back into her discussion about the biology? Part of the cruise was, as we talked about, it is indeed exploring, but it's also sampling and getting an overview of what is where and what lives where. So can you tell us a little bit more about that aspect?
Sure, you bet. A neat way to think about this vent field is that, as I said, a lot of where things live is controlled by chemical gradients. So if we think about the chimney itself, first we have, say, Oasisia tube worms, which enjoy high flow environments. They want to be up there where there's lots of hydrothermal fluid coming out. Those tube worms are able to handle the higher temperatures, and they're there to take advantage of the sulfide that's very abundant in that stream. Right? Then, as we look down that mineral structure of the chimney, there's lots of additional space for other organisms to settle that need to be farther away from that temperature, but that are still taking advantage of what the chemistry might be there. And I should clarify, so I say sulfide a lot, and then I distinguish between these and black smokers. There are also some other differences in these vent fields. We see a lot of methane in this system and a lot of other small carbon organic compounds, and that means that we have an even more diverse microbial community. And those microbes are often working together. They're often symbionts in the larger organisms. So as you look down that chimney, you'll find other organisms that are able to take advantage of, say, some sulfide and methane, but maybe not too much, right? Because sulfide is actually pretty nasty to a lot of organisms. You actually want to avoid it. Kind of like, it's not too foreign of an idea, because it's sort of like too much oxygen is actually bad for you, but we actually need it to breathe. And it's the same for these organisms. And then as you keep going out, you'll start finding things like clams, which again need some sulfide, but cannot tolerate the high sulfide. So that distribution of the community becomes very apparent. And that's a very simplified view of the system.
No, of course, but that also, it's a good segue to one of the questions we just got when you use the term distribution. One of the questions we have is, how do the organisms compare here to organisms at, say, the East Pacific Ridge or vents along the Mid-Atlantic Ridge?
That is a really interesting question. And actually, I was in a conversation just at lunch today about some of those details. One of the big, obvious, very visible differences you'll see is that here, our dominant tube worm is called Oasisia. And if you look at other vents, you'll often see the dominant tube worm is Riftia. It's just a different tube worm. So you might say, same thing, right? Well, no. And the biologists and, in fact, the geochemists are getting involved. The theory I heard is that maybe the Riftia actually are some of the first organisms to be able to come in and settle. They show up right away. But that Oasisia is actually able to take advantage of a lower flow, a smaller amount of sulfide over time. So maybe that means this is a more mature vent community, right? Maybe Riftia comes in at first and we've missed seeing that stage, but over time, Oasisia has been able to come in and outcompete, right? Because organisms need to be able to settle in the first place, but they also have to be able to compete for enough space. So that's one very easy to spot difference.
And so maybe this question is a bit ahead of where we're at with this, because it sounds like we have some baseline questions that need to be settled. Are the organisms that are living in these places, is it obvious that they are related to other organisms nearby? Does it look like these are kind of oases that just pop up and appear? Are they linked to other, kind of in a long family tree? Is that a discussion that's going on as well?
Well, you are jumping into the scientific fray, and that's also several very interesting questions. So the in terms of are they related to things close by, that's very interesting in the Pescadero Basin, because we actually have other types of vent fields that are really not very far away. We're talking tens of kilometers. And the traditional view of how organisms might be distributed and be able to settle into these environments. So imagine the small, very young versions of these life forms floating through ocean currents. Biologists have assumed that there was a range, but that it was a fairly large range that these organisms could be distributed. But as scientists have started to explore this region, these vent fields that are close together have very different groupings of organisms. And that's actually one of the driving scientific questions behind this particular cruise, is to try and figure out what exactly is controlling the community that we see.
That's cool. That's really, really interesting. We're actually getting sort of close to our time. And since this was based a lot towards the MATE ROV program, I wanted to sort of close out with a question without giving, again, we have a little bit of a limited time, but if students were trying to get in the positions where you are now, what advice do you have for them? I mean, if they want to be ROV pilots, do they need to be glued to computer screens and making their video game thumbs really dexterous? Do they need to be studying engineering? What advice do you have for folks to work on a research vessel?
To be honest, I mean, the ROV team is quite a diverse team. There is obviously the engineering element. There is some higher engineers. There's technicians. We have guys that have come in from the military. Basically, you've got to remember it's a team. So there's multiple skills. We need mechanics. We need electricians. We need electronics. We need computing. People who can operate computers, fiber optics. So there's definitely a wide range of skills in there, and every team is made up with a very different mix of people. Obviously, we always have to have one electrical, one mechanical, and one computing and our electronics. But really, there's no real right or wrong answer, because I've met so many guys from so many different industries that have come into ROVs, and they've got very varying skills. Not everyone's got a degree. Not everyone has technical qualifications. Some people have come in from like the military, and they've worked their way up that way. So there's definitely there's no finite way of doing it. But the one way to get into this game is the technical qualifications are very helpful. So it's helpful to have something like a diploma in electrical or mechanical or something like that, and then just get some field experience. Try and get like an internship, or try and get some work experience working on some kind of research vessel, but not necessarily research. There's also renewable energy. There's other elements to it as well. But that's kind of what I would do, in my opinion. I mean, none of us are really coming from any specific background. It's a very mixed affair.
Well, it sounds like with a lot of different needs, there are a lot of different skill sets you can bring to that. Is Deb still around? Can she talk about what again, sort of different tracks you can take to work on a research vessel?
Yes, so a lot like what Russ said, there are a lot of backgrounds within the marine tech field or other jobs within the ship. We have deck officers, we have engineers, we have chefs, we have stewardesses, we have MTs. Even within the MT department, we're a very diverse field. Some have strengths in more electronics or equipment, and some have more strengths in mapping and data. And so really it's about getting field experience, exactly how Russ said. And I can say that I started in 1999 as a MATE intern. And so one of the really important things to do is when you are in college or even not through college, really reach out and to try to get the opportunity to get on a ship. And MATE really provides that opportunity with their summer internships. So I highly recommend that. But there are a lot of avenues that you can do to get onto a ship, not just in the technology field. And even if you don't go in the technology field, even if you become a business major or a finance major or somebody, really just support the ocean research. And you may find that you are not necessarily, we've had artists at sea, we've had students at sea, we've had media people at sea. So you don't have to be a scientist to come to sea.
And I promise I did not know that you were a MATE intern before I asked that question. I really wasn't trying to plug the program, but it is true that MATE does have an intern program. And anyone that's interested, definitely needs to go to the MATE ROV website and check that out. For those of you who don't have a whole lot of knowledge with it, it's a program that focuses on robotics, and there's a very big competition where lots of students come together and switch ideas. It's a really, really great program, so we definitely encourage you guys to check that out. We are sort of getting close to the end of our time. Becca, do you have a few minutes to tell us a little bit about how you ended up on this vessel, your background, and how someone could possibly take your job from you in 10 years?
Sure, you bet. I have had a very wandering path. Although the older I get, the more I realize wandering paths are more common than you think when you're young. So I got very interested in science at an early age. At the age of 10, I decided I wanted to go into space. So I worked very hard for a lot of years thinking I wanted to be an astronaut. I also made some rather bizarre choices relative to that. So I knew I wanted to study science. I went to college, started studying biochemistry, and then heard that there was a field trip to go scuba diving in the Virgin Islands in January. And I said, sure, I'll be a geology major to get to go do that. I thought I would drop it. And it turns out I fell in love with field science and crazy exploring geologists. So I did that thinking maybe I was leaving space behind. But then it turns out that one of the places that is the best analog on Earth for working in space is underwater. So quite by accident, I got back involved in working underwater. So I have a history of many science trips on research vessels. I have worked in a lake in Canada, piloting deep worker submersibles. I finished my PhD in postdoc and said, oh, I don't know if I want to be faculty. And so then I started working as a science educator. Bizarrely, then I ended up back on a research vessel. So there just is no one given path. If you follow what you're interested in and pay attention to what you enjoy, I think you'll end up in the right place.
Awesome. That's wonderful to hear. So if those folks who are interested in taking steps on that path, we really do encourage you. This conversation here has to end, but please keep it going. Online, if you want to learn more about the MATE program, it's at marinetech.org. And to follow along with what Schmidt Ocean is doing, we are at schmidtocean.org. All of us have Facebook, we have Twitter, we have Instagram. So please do, if you have questions, follow up with us and keep the conversations going. We will be having more live conversations and more live streams from this expedition. Please, again, check out the website at www.schmidtocean.org. And for more information about robotics and the MATE competition program, please check out marinetech.org. Thank you very much, everybody.